Hello everyone. I'm Raunaq, and today I'm going to be talking about ReSkin, which is this new tactile sensor that we're super excited about, and hopefully you'll be excited about by the end of this talk. Let's start with some context. So if you think about the way we as humans interact with the world, we have a rich set of modalities like vision, audio, as well as touch. But if you look at the way our AI systems right now interact with the world, we see that we're largely restricted to vision and audio. And touch is something that is conspicuously absent from the way our AI systems interact with the world. Even more surprisingly, if we think about robots that we expect to continually physically manipulate things in the world, we see that we're largely relying on just vision and sometimes audio, but never touch. As humans, we know that touch is fundamental to the way we act and react to objects in our environment. So that begs the question, why can't our robots feel touch the same way? Well, our hypothesis is that it's because we lack a viable tactile sensor in AI and robotics right now. And to talk a bit more about this, I will start off with what a good tactile sensor looks like. And I think we can start with an example that we're all familiar with, which is human skin. And the properties of human skin, if I list them out, is it's conformal. So it deforms around the object it's trying to grasp and has a stable grasp. It's regenerative. Since human skin is soft, it can cut, tear, bruise, and being regenerative allows it to continue to act as an effective tactile sensor. It has low thickness, so it's not obstructive when it's trying to cover like thinner parts of our body, like eyelids, for instance. It enables large area sensing, so we basically have sensing all over our bodies, and that sort of gives us a rich tactile signal when we're interacting with the world. And it operates at a high frequency, going up to around 400 hertz for the kind of reactive control that we do in our daily lives. And if you think a little bit more about AI and robotics and what a good sensor looks like for robotics and AI, like Nando said in his talk earlier today, data is the core of machine learning. And so we'd ideally want a sensor that is low cost so that we can collect these large quantities of data in different settings. We'd want something that's durable. So sure, we want our sensors to be replaceable, but we don't want to replace them every 5 minutes. And we'd like something that has data reusability, by which we mean that when we have multiple instances of the sensor, we would like to be able to pull the data and train models that actually generalize to new sensors. And so if you look at how existing tactile solutions fare up against these characteristics, we have optical sensors, which are really popular right now with gel side, digit, and the like. And these are very promising because they offer conformal contact. They're pretty replaceable. They're not that expensive, and they're reasonably durable, even though there is no real study that's been done to clearly support that. But where they fall behind is in terms of that form factor, because they're kind of thick because of the camera's depth of focus, and they don't quite have a straightforward way of enabling large area sensing. Of course, the frequency is like 60 FPS, so that's much lower than the frequency at which we know human skin operates. The other set of popular sensors in robotics is the biotac sensor, and this similarly offers conformal contact and offers pretty high frequency for a tactile sensor. And it's industry grade and it's pretty durable. But again, the problem is the form factor. You can't really put it on arbitrary surfaces you might want to cover with tactile sensors. And it's pretty expensive, so it doesn't really scale very well in terms of just having multiple tactile sensors in different applications. And the third set of really promising recent alternatives is these piezoresistive fabrics, which are nice in the sense that they finally allow us to do large area sensing without adding much thickness to whatever we are trying to sensorize. But the problem with them is generally that they have too many failure points, and therefore they're not as durable as we would want our tactile skins to be. So this is where, if you look at this table, you see that there is no single sensor that satisfies all of these characteristics, and this is where ReSkin comes in. So ReSkin is this inexpensive, replaceable, and long-lasting tactile skin. But more importantly, what we think makes ReSkin special is that it comes in all shapes and sizes. The form factor, you can have whatever form factor you'd like to have. And that's what enables us to use ReSkin for a lot of applications. Like, for instance, we put it in a dog shoe, and that's Millie just going around the way she normally would if the video was playing. But trust me, she can walk around without any trouble, even though we've got a sensor in the dog shoe. And that allows us to collect a lot of interaction data between her paws and her gait patterns as she moves around the class. Then this is where we similarly sensorized a nitrile glove with a ReSkin sensor and collected interaction data while packing a red bean bun. And you can see that it's sort of like, because it's so thin, it's not obstructive, and it does not become inconvenient as you do something as involved as that. Similarly, if you wanted to cover a larger area, ReSkin's got you covered. We sort of made this arm sleeve which was sensorized over an entire surface, and this is like a coarse contact localization over that. And if any of y'all are interested in robotics, you can always add ReSkin to your end effector, and that to get this sort of low-level feedback, and that will allow you to pick up, like in this case, pick up delicate objects like blueberries without squishing it. I promised you I would not put the video there if the one with the feedback also squished the blueberries, but it's just not running right now. And so I'm just gonna move on. So hopefully this is convincing, and you're wondering, okay, fine, all this is cool, but what exactly is ReSkin and how does it work? So the idea behind ReSkin is actually pretty simple. I think the clicker is not working. Okay, yeah. So what ReSkin contains is a magnetic skin, which is an elastomer with embedded magnetic microparticles. And underneath that is a circuit board that contains magnetometers. And the way it works is whenever you have an object that comes in contact with this deformable elastomer, the elastomer deforms and moves the magnetic particles with it. And that causes a change in magnetic flux, and that's basically what the magnetometers read out as an output. So if we go back to the set of characteristics we listed initially about what a good tactile sensor looks like, we see that ReSkin is conformal. It's not quite regenerative, but it's replaceable. So if you have a cut or your surface gets damaged because you're interacting with something that's hard, it's pretty easy to just take off an old skin, put on a new skin, and continue doing whatever you were doing. It's pretty thin. So it's less than 3 millimeters thick, so it's not going to be obstructive when you're trying to sensorize something. It enables large area sensing, like I already showed with that arm sleeve earlier. And it operates at a pretty high frequency, going up to about 400 hertz, which is actually finally reaching the kind of frequencies that human skins can detect. And in terms of the characteristics for ML, it's low cost. It costs about $6 per sensor, so it would be easy for people to have a lot of these sensors and sensorize everything they want to with this. And in terms of durability and data reusability, I will come back to this in a bit more detail, but I'll take a small segue to talk about how useful is the ReSkin signal and what does it look like. So to understand this, we do a small experiment where we take a robot arm, a force sensor, and an indenter, and we put them together in a setup that looks something like this. So what's happening here is that indenter is going to press against the skin in a pattern that looks something like that, and we collect data for like the force location and the force magnitude, as well as the magnetic flux that we're getting from the sensor. And we train a neural network that does these predictions trained on mean squared error. And we see that we're able to hit about 99.5% accuracy in terms of just localizing within a millimeter. And our root mean squared error on the force is under a 0.1 Newton, so we can do pretty fine force prediction as well. But now, if I come back to the question of durability, one of the biggest problems with soft materials is that their properties drift over time. So what happens to our models when this drift happens? Like, do they continue to work? So to understand this, we do another experiment where we collect data from 40,000 indentations made the way I just described, and we train this on the first 5,000 indentations. And then what we do is we test this on a set of 1,000 indentations at intervals of 5,000. So we're testing on indentation number 5,000 to 6,000, 10,000 to 11,000, 15,000 to 16,000, and so on. And if we plot the mean squared error, so the blue plot here is mean squared error for the XY localization, and the orange is force, we see that we are still able to retain sub-millimeter accuracy over 35 to 40,000 iterations. And the force, I will go into a bit more detail with this other plot that is essentially, we take these 1,000 samples after 35,000, and we plot the prediction versus the true force. And we see that we sort of have this like constant offset where our model is overestimating the force consistently and continues to retain the ability to sort of distinguish higher forces from lower, like relative higher forces from lower forces. So presently, we don't do anything about this. This offset is easy to learn, but which should be fairly easy to learn. And we believe that the relative magnitudes is what we're going to need in most applications where we use this sensor. And in terms of replaceability, so what happens to our models when we take a skin out and put a new skin on? Like, how well does that work? So if you just naively take a model that was trained on a single sensor and test it on another sensor, it doesn't work as well. So we have a mean squared error of like 6 millimeters square, and in force, it's like 0.4 Newton square, which is pretty bad. But if we do the next most obvious thing, that is we train from a large number of skins, then we're able to get back to sub-millimeter accuracy, and our error on the force also drops to around a third of what it was. And this seems like an obvious solution, but for the longest time in soft robotics, this has been a problem because there's often too much variability in your fabrication process to be able to do something like this, or your fabrication process is so complex that you cannot actually make multiple instances of your sensor to be able to do something like this. And this worked pretty well, so we were like, can we do a little bit more than this, where if you're replacing a skin, is there a simple calibration procedure you could have? And turns out there is. So what we did was this self-supervised calibration procedure, where first we break this neural network down into two components, a feature extractor and an output model, and we add this thing called a triplet loss to our training loss. And the triplet loss is pretty simple. So if you have these indentations in a line, you identify a set of 3 points, here called the anchor, the positive, and the negative example. And essentially, you make sure that since the anchor and the positive point are closer to each other than the anchor and the negative, you try to get the features of the anchor point closer to the positive example than the negative example. And so at calibration time, what you can do is just make indentations in a line along the sensor and just fine-tune these already trained models with this triplet loss without needing to explicitly have labels. And what this does is allows us to get over a 30% improvement in our localization and 8 to 9% improvement in terms of our force prediction. And that's what makes ReSkin truly replaceable. So to summarize, if we look at all the characteristics that we initially listed, we believe that ReSkin is actually able to meet all of the requirements of a good tactile sensor. But most importantly, ReSkin is versatile and can be used across a wide set of applications. So we hope that all of you and like the robotics and AI community in general will try to use this sensor and collect a whole bunch of data that will help us move forward with a good tactile sensor. Thank you.
Thanks very much. And Raunaq, you're going to be giving a demo of this week,
yes, we will have a demo of this. I don't have it with me right now, unfortunately, but we'll be here at both slots during the Wednesday demo sessions to give quick demos of these skins. And if people want samples, they can also talk to us, and we could arrange that as well.
Great. OK, are there any questions from the in-person people? There are no questions from the virtual world. So down here, we have a question. Hermane. I'll just say the question for people at home. So the question is, how does it work when you have other sources of electromagnetic field?
Yes, it should be OK with other sources of electromagnetic fields, because what it functions on is change in flux as opposed to just raw flux data. So if you had a constant offset over there, it will be fine. So for instance, like the Earth's magnetic field changes from like Pittsburgh, where we came from, to London. And it's fine because it just functions on change in magnetic flux. But if there were magnetic objects, that it might be a little more problematic. If there are ferromagnetic objects, it would still be OK, because then instead of detecting the deformation of the skin, the magnetometers are actually detecting the proximity of the ferromagnetic object. And so, I mean, you'd have to retrain your model there, but you would still be able to do something useful with that.
OK, thank you. We don't have time for any more questions, but please go and see Raunaq at the demo session on Wednesday. Thank you very much.
Thank you.